Welcome to the Deep Dive, your shortcut to being truly well-informed. Ever wondered what it really takes to keep, those complex digital systems running smoothly?
Yeah, the stuff behind the websites and apps we use constantly.
Exactly. Today, we're plunging into the core of it, mastering process management in Genie Linux. And we're looking at it through the eyes of a Red Hat certified system administrator, an RHCSA. So whether you're prepping for a meeting, trying to get up to speed on something new, or just plain curious, this deep dive is designed to give you that vital strategic understanding.
In our source material today, it's basically a comprehensive guide to Linux process mastery, specifically at that RHCSA level.
Okay.
It really goes beyond just listing commands. It focuses more on the strategic thinking, the oversight you need for managing these, well, pretty intricate systems.
Right.
We'll cover the basics, the commands everyone needs, but also get into some pretty sophisticated performance tuning and automation as well.
So, our mission today is to unpack those essential nuggets, maybe find some surprising facts about how processes actually behave and, how the experts manage to tame them.
Yeah, with precision and foresight.
So, the big question for you listening is, what does it truly take to manage the heart of a Linux system, its running processes, and keep things stable and efficient?
Well, to give you a roadmap, our source breaks down what an RHCSA needs to master into several key areas. Think of them as, like, building blocks.
Okay, lay them out for us.
First up, just plain proficiency with fundamental commands. Tools like ps, top, maybe htop.facetree, killer. Also, nice, bgf, gjobs, all the basics for viewing, controlling, prioritizing tasks.
Got it. The toolkit.
Then there's what you might call the art of process management. This is understanding the details, process states running, sleeping, zombie interpreting hierarchies, signal handling, the subtler stuff.
Okay, more than just typing commands.
Exactly. Then job control, managing foreground and background tasks, suspending things with crdl plus z. Then process monitoring, using commands like pso, top, free, uptime, vmstat, iostat, sar, all tools to track resource usage, CPU, memory, disk I/O, and spot bottlenecks before they become big problems.
Makes sense. Keeping an eye on things.
Then system resource limits, setting guardrails using ulimit or configuration files like etcetera-security-limits.conf, even kernel parameters via syscalDL. We'll talk soft limits versus hard limits.
Right, preventing chaos.
Then job scheduling, automating tasks with cocron, understanding its syntax. Also add batch. And we should briefly touch on modern system timers too.
Automation, always key.
Yep. Then process accounting, using PSACT or ACT to track who ran what, when, and how much resource it used. Analyzing history with last common psi.
Like auditing for processes.
Kinda, yeah. And finally, system performance tuning, identifying and fixing bottlenecks, CPU, memory, disk, network, using a whole suite of tools like vmstat, sar, systel, insftool, and analyzing logs for proactive optimization.
Wow, okay. That's a lot to cover.
It is, but it paints the full picture.
So this deep dive should give you a really comprehensive understanding of what an RHCSA actually does to keep systems stable, efficient, and resilient. All right, let's unpack this.
Let's do it.
So starting with those absolute basics, right? The command toolkit every RHCSA depends on. You said step 1 is proficiency with fundamental commands.
That's right.
Like PS, that gives you the static snapshot, the list of what's running.
Exactly. And PO is particularly useful, like you said in the outline, showing all processes, who owns them, CPU, memory usage. It's like that detailed passenger list.
Okay, but it's static. What about seeing things happen live?
Right. For the dynamic view, you need top. Or HTOP, which many people find a bit friendlier. These give you a real-time dashboard. You see what's happening right now. You can spot resource hogs instantly, even kill processes directly from top to HTOP.
So if something starts eating all the CPU, top shows it immediately.
Instantly. Then there's tree. That one's neat because it shows the parent-child relationships, like a family tree for your processes.
Ah, okay. So you see how things are connected.
Yeah, crucial for understanding dependencies, especially if you need to stop something. Which brings us to kill and kill all.
Right. And the source mentions signals are important here. What's the deal with sigterm versus sigkill?
Ah, yeah, that's a critical difference. Sigterm is the polite way. It sends signal 15, basically asking the process, hey, could you please shut down cleanly?
So it gets a chance to save its work.
Exactly. Save files, close connections, exit gracefully. Sigkill, which is signal 9, is, well, it's the sledgehammer.
Okay.
It doesn't ask, it just terminates the process immediately. No chance of cleanup.
Which could cause problems, I imagine. Data loss.
Absolutely. data loss,
Hmm.
orphaned resources, maybe leaving the system in an inconsistent state. So knowing when to use SIGTERM first is, like we said, the start of the art. You try to be gentle.
Gentle when you can, decisive when you must. Got it. Okay, what about managing multiple tasks in just one terminal? That sounds useful.
That's where job control comes in.
Yeah.
Commands like beg that resumes a stop job in the background. FG brings a background job to the foreground. And jobs just lists your current background jobs. It lets you multitask without opening, 10 different terminal windows.
Like putting a call on hold?
Pretty much, yeah.
Yeah.
You hit Control plus Z to suspend the current foreground job. Then maybe type big to let it continue in the background while you do something else. Then FG brings it back when you're ready.
Nice. And you mentioned nice and renice for priority.
Right. Nice starts a command with a specific priority, and renice changes the priority of something already running. Lower niceness value means higher priority.
So you can make sure important stuff gets the CPU.
Exactly. Give your critical processes the fast lane.
Right.
Maybe slow down something less important that's eating resources. It's about orchestration.
Okay. That definitely feels like moving beyond just typing commands into that art of process management you mentioned earlier.
Precisely.
What else does that art involve? You mentioned nuances.
Yeah, it's about understanding the process life cycle more deeply. Processes aren't just running or stopped. There are other states.
Like what?
Well, a process can be sleeping. Usually that means it's waiting for something, maybe user input, maybe data from the disk, network I/O. Most processes spend a lot of time sleeping, actually.
Okay. Makes sense.
It can be stopped, like when you hit Shittable plus Z, it's paused, not terminated. And then there's the zombie state.
Zombie. That sounds bad.
It's fascinating, really. A zombie process is one that is finished executing, it's terminated, but its parent process hasn't acknowledged its termination yet, hasn't collected its exit status.
So it's dead but still hanging around.
Exactly. It's not using CPU, but it still occupies an entry in the process table. If you get too many zombies, maybe due to a poorly coded parent process, you could potentially run out of process IDs, preventing new processes from starting.
Wow. So it is bad. A silent killer, like you said.
Yeah, potentially. So spotting these different states with keeps or top is key to diagnosing weird system behavior.
And this understanding feeds back into using signals correctly, right? Like not just jumping to sick kill.
Absolutely. A good admin, an RHCSA, wouldn't just kill -9 something immediately. They'd maybe use STRI first to see if it's apparent to other important things.
Check the family tree first.
Right. Then they try SIGTERM, signal 15, to ask it to shut down nicely. Only if that fails, or if the situation is critical, would they resort to SIGKILL, signal 9. That foresight avoids destabilizing things unnecessarily.
So it's strategic thinking. What else falls under this art? Resource limits?
Definitely.
Yeah.
Managing resources proactively. We mentioned nice and realize CPU priority, but also setting those hard limits using ulimit or more permanently in etcetera.securitylimits.com.
Those guardrails we talked about.
Exactly. Setting maximum memory usage or the maximum number of files a process can open, no file, or maximum CPU time. It stops one runaway application from bringing down the whole server. But you need to understand the application's needs too, not set limits too low. It's a balancing act.
Okay, balancing protection and function. And automation fits in here too, right?
Yeah.
Job scheduling. That sounds indispensable for being proactive.
It really is. An RHCSA absolutely has to master cron for recurring tasks.
Yeah.
Editing those cron tab files using cron tab E and understanding that 5-field syntax is key. Minute, hour, day of month, day of week. Get that wrong, and your job runs at the wrong time, or not at all.
Right, like that backup example. 02 path to backup script .esh daily at 2 a.m.
Precisely. And verifying it ran by checking the logs is just as important. Then for one-off tasks, you have at and batch.
How they differ?
At runs command at a specific time in the future. At now plus 10 minutes, for example. Batch is a bit smarter. It runs the job when the system load average drops below a certain point, usually 0.8 by default.
Oh, neat. So it waits for a quiet moment.
Yeah, perfect for heavy tasks. You don't want impacting users during busy periods. Managing these scheduled jobs, making sure they run reliably, that's a core part of keeping a system maintained with minimal fuss.
Set it and forget it. Ideally.
Well, set it and verify it, then forget it.
Good point. Okay, that leads nicely into process accounting and performance tuning. This sounds like looking backwards to move forwards.
That's a good way to put it. Tools like PANSACT or ACT, depending on your Linux flavor, log every command that runs, who ran it, when, how much CPU and memory it used.
The system's diary.
Pretty much. And you analyze that history with SA, which gives summaries, and LASCOM, which shows individual command executions. You can spot trends, identify inefficient scripts, or even detect security anomalies over time.
And performance tuning uses tools like VMstat, IOStat, SAR.
Right. They give you the current and historical data on CPU load, memory pressure, disk activity, network traffic, all the vitals. Identifying bottlenecks with these tools guides your optimization efforts, maybe tuning kernel parameters with sysintl, or changing process priorities, or even recommending hardware upgrades based on hard data. It's forensic analysis for performance.
So you're not just guessing what's slow, you're proving it.
Exactly.
Let's circle back to job control for a sec. We mentioned VG, FG, jobs, C+L plus Z. How does an RHCSA really master this beyond just knowing the commands?
It's about seamless workflow, really. Fluid context switching. That example of compiling something big.
Right, takes ages.
Yeah. And then, bam, an urgent config change needs doing now. You don't want to kill the compile. So C+L plus Z suspends it instantly.
Pauses it.
Right. Then B pushes it to the background, still pause, or maybe running depending on the shell. You do your urgent task.
Yeah.
Then later you type FG, maybe FG +1 if it's job number 1, and your compilation comes right back to the foreground, pick up where it left off.
Slick.
It saves a ton of time and hassle. Mastery means knowing the job numbers, knowing how to manage multiple background tasks without confusion, maybe using kill +1 with sigterm to gracefully stop a background job if needed.
So signals apply to background jobs too.
Oh yeah. You might need to send sigterm to job number 2, for instance. And again, STRI can be useful here to understand dependencies before you suspend or kill something that might be running in the background.
Makes sense. And this ties into automation too.
Definitely. Those cron jobs, at jobs, batch jobs, they often run in the background. So understanding job control helps you manage and troubleshoot them too. Verifying they executed correctly via logs is part of managing those background automated jobs.
So it's not just interactive sessions, it's the whole life cycle.
Right. And resource monitoring plays a role. Is that background batch job using too much I/O? IOStat might tell you. Process accounting, PSAC, tells you how much resource it used after it ran. And setting limit restrictions might be necessary even for background or scheduled jobs to prevent them from going haywire.
It all connects. So troubleshooting a stalled background job involves pulling all these tools together.
Absolutely. You might check system load with uptime or VMstat, check I/O with IOStat, check its priority with PS or top, which shows niceness, maybe attach strace to it.
Strace, what's that do?
Strace is powerful. It traces the system calls a process is making and the signals it receives. It's like listening in on the conversation between the process and the kernel.
What?
Yeah. If a process is stuck waiting for a file or a network connection, Strace will often show you exactly what it's waiting for. Invaluable for debugging weird hangs.
Okay, that sounds like deep magic.
It feels like it sometimes. But mastering job control, combining it with monitoring and troubleshooting tools like Strace, that's how admins keep complex environments humming along smoothly.
All right, let's shift focus specifically to monitoring, keeping that eye on the system. Beyond Ipsen TOF, what does effective monitoring really look like for an RHCSA?
It's about depth and breadth. So EAP, for that detailed snapshot, yes. The EAP-seal is another common one, good for seeing process IDs, parent PIDs, and start times, often showing the full command line.
And STRI for the hierarchy again?
Always useful for context.
Yeah.
But then you get into resource-specific tools. For memory, free is essential. It shows total, used, free memory, but also, crucially, buffers and cache and swap usage. High swap usage is often a red flag for memory pressure.
Okay, so free tells you if you're running out of RAM.
Or relying too much on slow disk swap. Yeah. Then uptime gives you those load averages 1, 5, and 15 minutes. They give a quick sense of overall system load or stress. High load doesn't always mean CPU problems. It could be I/O weight.
Okay, so load average isn't just CPU.
Nope. And that's where VMstat and IOStat come in. VMstat gives you snapshots of processes, memory, swap, I/O, system, and CPU activity. That percent of weight column in VMstat is golden. It tells you the percentage of time the CPU was idle because it was waiting for disk I/O to complete.
So high percent weight means slow disks are likely the bottleneck?
Very likely, yeah. IOStat gives you even more detail on disk activity per device. Throughput, operations per second, average wait times, essential for diagnosing storage issues.
And SAR, you mentioned that for history.
Right, SAR, System Activity Reporter, is part of the systat package, same as IOStat. Its power is collecting and reporting historical performance data. You can run SAR-U for CP history, SAR-R for memory, SAR-SAR-B for I/O over days or weeks.
So you can spot trends or see what happened last Tuesday at 3 p.m. when things went slow.
Exactly. It's invaluable for correlating performance issues with specific times or events rather than just looking at the current moment. Game changer for long-term analysis.
Wow. Okay. And logs are part of monitoring too, right? Where do you look if a process just dies?
Absolutely critical. Djere's shows you the kernel range buffer, good for low-level stuff, hardware errors, drivable problems. But for most application or service issues, you'll use journal Hopital on modern systems using system. Journal Hopital, a Jew service name, shows you the logs specifically for that service. If something crashed, the errors are usually right there. Cross-referencing log timestamps with SAR data or top output is how you piece the puzzle together.
Makes sense. Any other key monitoring tools?
Elan is another great one. It lists open files. Since everything is a file in Linux, this can show you open network connections, which libraries a process is using, which data files it has open. Really useful for tracking down resource leaks or figuring out what a process is actually doing.
Okay. And for really deep dives, like strace.
Yeah, strace for system calls. And PMAP is another advanced one. PMAP-X PID shows you the memory map of a process, how it's using its virtual address space, which libraries are loaded where. Good for diagnosing memory-related issues like leaks or segmentation faults.
So monitoring is really about using the right tool for the job, from high-level overviews to deep diagnostics.
And combining the information from multiple tools, plus automating some of it.
How so?
Well, you might set up cron jobs or system timers to run SAR periodically to ensure data collection, or write simple scripts triggered by cron to check load average or free memory and send an alert if thresholds are exceeded. Proactive monitoring.
The system watching itself. Very cool. So if CPU usage spikes, you correlate top SAR, maybe process accounting, logs.
Exactly. Check priorities with NICE, check limits with ulimit, check disk weights with IOStat or VMstat. It's detective work, using all the clues these tools provide to maintain that efficiency and reliability.
Got it. Okay, let's talk resource limits, setting those guardrails. You mentioned soft and hard limits and ulimit.
Right. So ulimit is the command you use in the shell to view or set resource limits for the current session and its child processes.
Temporarily, then.
Yeah, usually temporary. You can query limits with ulimit A or set a soft limit, say, on the number of open files. Ulimit SNSN 4096, ARS for soft, H for hard.
What's the difference again? Soft versus hard.
The soft limit is the currently enforced limit for a process. The process can often raise its own soft limit up to the ceiling set by the hard limit. The hard limit is the absolute maximum. Usually only root can raise a hard limit.
Okay, so soft is the current rule, hard is the absolute maximum possible.
You got it. And for limits that stick around after you log out or reboot and apply more broadly, you need to configure files. The main one is etcetera-securitylimits.conf.
Right, the permanent highway speed limit.
Exactly. In limits.conf, you specify limits per user, per group, or globally using Brain. You set items like no file, open files, mproc and number of processes, memlock, memory that can be locked, CPU time in minutes.
So you could say user Webuser can only open 10 to 34 files max.
Precisely. Like Webuser soft no file 2024, and maybe Webuser hard no file 2048. You need careful syntax there specifying the domain, user group, type, soft hard, item, and value. Modern systems also use files in etcetera-securitylimits.d, which override limits.conf.
Good to know. Keeps things modular. And this prevents bad things from happening.
That's the goal. Prevent resource exhaustion, stop fork bombs, where a process rapidly creates copies of itself, overwhelming the system with too many processes, limiting nproc helps here. Limit core dump sizes, so they don't fill up disks. It's about stability and security.
And there are kernel-level controls, too, using SICTAL.
Yes. Well, limits.conf sets per user or per process limits, SICTAL tins kernel parameters that often affect the entire system.
Like what?
Things like the maximum total number of open files the kernel will allow, fs.filemax, or network buffer sizes, net.core.rmmmax, or virtual memory behavior, vm.swappiness.
VM swappiness.
Yeah, it controls how aggressively the kernel swaps memory pages out to disk. A lower value means it prefers to keep things in RAM. Higher means it swaps more readily. Tuning this can significantly impact performance depending on the workload.
Interesting. And you make these changes permanent how?
You edit at etcetera-sectl.conf or files in etcetera-sectl.d, then run sestl-pp to load the changes from the file immediately. It's tuning the OS core itself.
So you have user limits and system-wide kernel limits working together.
Exactly, a layered approach. And you need to monitor that these limits are working and appropriate.
How do you monitor the limits specifically?
Well, you can check current limits with ulimit A. You can use time path to command to see resources used by one command execution. LSOF helps see how many files a process actually has open.pmap for memory usage. And again, SAR for historical trends, VMstat, IOstat for real-time bottlenecks, process accounting, logs, resource usage too. It's about seeing if processes are hitting the limits you've set.
And troubleshooting if they do, like the too many open files error.
Right. If you see that error in logs, var log messages or journal MLO, you need to check and likely increase the no-file limit for that user or service. Using limit temporarily or limits.cons permanently. It's about connecting the error message back to the specific limit that was hit.
Okay, that makes sense. It's a core part of making the system resilient.
Absolutely. Prevents accidental overload and makes things harder for malicious actors, too.
All right, let's move to job scheduling. The unsung hero, you called it. Cron is the big one here.
Definitely the classic. Cron is the daemon that runs scheduled commands. Users manage their schedules using cron tab files. Cron tab, DAIE, edits your personal cron tab.
And that 5-field syntax,
Right,
minute,
boy.
hour, day of month, month, day of week.
Got it. Plus the command to run. Asterisk means so command runs every minute, zero command runs every hour on the hour. Getting that syntax right is crucial. Cron tab DLAA lists your current schedule.
And system-wide jobs.
Those usually live in @cron tab, which has an extra field for the username to run as, or as individual files in @cron.d. Admins need to manage these too. Verifying execution is key check logs like varlog cron, or use journal.tl to see if the job ran and if it produced errors.
So precision timing for regular stuff. What about the one-off tasks again? At and bash.
Right. is for run this command once at this specific time, like echo reboot at 2 a.m. tomorrow. At queue lists, pending at jobs, at queue term removes them. Batch is similar to but it runs the job only when system load permits, as we discussed. You just pipe commands to batch. Good for non-urgent, heavy tasks.
Got it. Now, you mentioned systemed timers as a more modern approach. What's the advantage there?
Yeah, system timers are increasingly preferred. They offer tighter integration with the rest of the systemed ecosystem. Well, each timer is typically paired with a service unit that defines what actually runs. This gives you much better control over the execution environment, dependencies, resource limits, using C groups, and especially logging. Journal Tickle automatically captures the output of jobs run via system timers, making debugging way easier than parsing cron logs or dealing with mailed output.
Better logging and control. Sounds good.
You define the schedule using directives like onCalendar, similar to cron syntax, or onActiveSec, run after activation, inside the .timer file. Then you would enable and start the timer unit just like any other system unit. System Terl enable now mytask.timer. System Terl's list timers shows active timers.
So potentially more robust than cron?
Often, yes, especially for system services or complex jobs, though cron is still widely used and perfectly fine for many tasks. And RHCSA needs to know both.
Okay. What about the environment these jobs run in? You mentioned scripts might fail when automated.
That's a super common problem. The environment for cron jobs or system timers is often very minimal compared to your interactive shell. Path variable might be different, other environment variables missing.
So your script can't find commands it normally finds.
Exactly. Best practice is often to use absolute paths for all commands within your scripts. Use bingrep instead of just grep, or explicitly set the path at the beginning of the script or in the cron tab file itself. Permissions are another big one. The job runs as needs, read, write, execute permissions on everything it touches.
Right. And who can run cron jobs? Can any user?
You can control that with etcetera.cron.allow and etcetera.cron.deny. If cron.allow exists, only users listed there can use cron. If it doesn't exist but cron.deny does, users listed there are blocked. If neither exists, usually only root or all users can use it, depending on the system config.
Okay. Access control. And troubleshooting failed jobs. Check logs, run manually.
Yeah. Check varlog cron or journal tool. Try running the exact command or script manually as the user of the job runs as to replicate the environment as closely as possible. Oh, and one more tool, Anacron.
What's that for?
Anacron is designed for systems that aren't running 247, like laptops or desktops. It ensures that jobs scheduled to run daily, weekly, or monthly, usually via etcetera.daily, etcetera.weekly, etc., still get run even if the system was off at the scheduled time. It runs them shortly after the system boots up if they were missed.
Clever. Catches up on missed work.
Exactly. So mastering all this CRECRA, batch, system timers, troubleshooting, Anacron, it's about ensuring reliable automation, minimizing manual work, and keeping the system ticking over smoothly.
Foundational indeed. Okay. process accounting. You called it a deep dive into what actually happened, the system's ledger.
Yeah, using tools like SACT on Red Hat-based systems or ACT on Debian Ubuntu,
Yeah.
you need to install the package and usually enable and start the service, PSACT or ACT.
And it just starts logging everything.
Pretty much. It logs process completion records to a file, usually var-account packed. This includes the command name, execution time, user ID, terminal, CPU time used, memory used. Quite detailed.
Okay. So how do you make sense of that raw data? You mentioned the LASCOM and the SAC.
Right. LASCOM reads the accounting file and shows you records in reverse chronological order. You can filter it, like LASCOM root to see commands run by root, or LASCOM command backup.sh to see executions of a specific script. Great for auditing who did what when.
Okay, that's useful. And SAW.
SAW summarizes the accounting data. It can show you total system time per command, number of times each command was run, average memory usage, sorted in various ways. SAW might show you per user summaries. It helps identify which commands or users are consuming the most resources over time.
So LASCOM for individual events, SAF for the big picture trends.
Exactly. You might use SAW to find the top 10 CPU-consuming commands over the last month, for instance, or spot if a user is suddenly running unusual commands via LASCOM.
How does this fit with security auditing? Does it replace tools like Audit?
It complements them. Audit is often focused on specific security events, system calls, file access according to defined rules. Process accounting gives you a broader, less targeted log of every completed process and its resource usage. Correlating LASCOM output with audit logs or journal etcetera can give you a very complete picture when investigating an incident or troubleshooting a weird issue.
Like confirming if a scheduled backup actually ran and how long it took?
Perfect example.
Yeah.
Check LASCOM to see if backup.sh completed. Check SA to see how much CPU and memory it typically uses. If it failed silently, the accounting logs might hold clues.
And this feeds into performance tuning, too, looking back to improve.
Absolutely. If SA shows that a particular data processing script is consistently using huge amounts of memory or CPU, that tells you it's a prime candidate for optimization. Or maybe it indicates you need to adjust its NICE level or set resource limits via limits.com so it doesn't impact other services. It provides the historical data to justify tuning efforts or even hardware upgrades.
Can you automate reports from this?
Well, yeah. It's common practice to set up cron jobs to run Serifol periodically, maybe generate a daily or weekly summary report. You could also have scripts parse LASCOM output, looking for specific patterns like repeated failed logins or commands run outside of normal hours and trigger alerts. Turns that raw data into actionable intelligence.
Okay, super comprehensive. Finally, let's hit system performance tuning. This sounds like the pinnacle, right? Taking a working system and making it fly.
It's definitely where a lot of the deeper knowledge comes together. The goal is optimal resource use, responsiveness, reliability. It starts with identifying bottlenecks using those monitoring tools we discussed.
Yeah.
Top, HTOP, VMstat, IOStat SAR.
Reading the vital signs.
Exactly. Interpreting load averages, memory usage free, that crucial percent of weight from VMstat or IOStat network stats. Using SAR's history to see if performance degraded after a specific change or during peak loads. You need to know what the bottleneck is, CPU, RAM, disk, network, before you can fix it.
And kernel tuning with Systel is a big part of fixing things, that engine tuning analogy.
It often is. Adjusting parameters and proxies via sysdeal, we mentioned VM.swappiness. Others might include network stack tuning, like TCP buffer sizes, net.core.rmx, net.ipv4.tcp-rmam, or enabling TCP window scaling, net.ipv4.tcp window scaling, maybe increasing file system limits, like fs.file max if the system needs to handle tons of open connections.
And making those permanent in etcetera's tctl.com.
Right, and applying with sysdpl.fig. But you have to be careful, understand what each parameter does, change one thing at a time, and measure the impact. Blindly copying settings from the internet can easily make things worse.
Good advice. Change one thing, test. And resource limits, limits.com, are part of tuning too.
Definitely. Ensuring processes have the resources they need, but not so much they can overwhelm the system. Maybe you identify a memory leak using PMAP or Valgrind, and while fixing the code, you temporarily limit the process's memory with a ulimit to prevent crashes, or on UMA systems.
Non-uniform memory access.
Right, where different CPUs have faster access to different banks of memory. On those systems, using NUMAC to bind processes or allocate memory on the local node for the CPU core it's running on can give significant performance boosts for certain applications.
Wow, okay. Getting specialized there. What about disk I/O tuning? Beyond spotting bottlenecks with IOStat.
You can influence I/O priority using IONIS. Give critical database processes higher I/O priority than, say, a background backup job. You can test disk performance directly with tools like HTParm or DDD. Maybe tune file system parameters?
File system tuning?
Yeah. Choosing the right file system, XFS, XT4, etc., for the workload is step one. Then tuning mount options in etc. stab. Using no time or real-time can reduce disk writes by not updating file access times constantly. For XT4, Tune 2s can adjust parameters. For XFS, XFSinfo shows settings. Monitoring disk queue depths with IOStat-Next helps see if the storage itself is saturated. And checking drive health with SmartTech is basic maintenance.
A lot goes into storage performance. And network tuning, another rabbit hole.
It can be. Adjusting TCP settings via systicle is common buffer sizes. Congestion control algorithms, TCP congestion control. Using ethtool to check or set network card settings like speed, duplex, offloading features. Analyzing network connections and performance with SS, the monitor replacement for NetStat. Optimizing firewall rules so they're efficient, maybe even using TCE, traffic control, for quality of service, prioritizing interactive traffic over bulk transfers, for instance.
That's a huge range. How does automation fit into tuning?
You automate the monitoring part. Schedule regular SAR data collection, set up alerts using cron or system timers with scripts that check key metrics, maybe even automate some responses if you're confident, like adjusting nice levels based on load, though that's advanced. And for troubleshooting persistent issues, you pull out the heavy hitters. Strace, perf GDB, block trace for deep block I/O tracing, mstat for per CPU statistics. It's a continuous cycle. Monitor, identify, tune, measure, repeat.
Building that resilient, high-performing system, not just reacting.
Exactly. Proactive and data-driven.
Well, this deep dive really hammers home that mastering process management in Linux is, well, it's complex. It's definitely not just about memorizing commands.
Not at all.
It's that blend of technical skill, strategic thinking, almost detective work, like you said. Precision and foresight seem to be the keywords.
That's really the core of it, yeah. Understanding all these pieces, the commands, the process states, job control, monitoring, limits, scheduling, accounting, tuning it, gives you that powerful mental framework for how these systems actually work and how they're kept running reliably.
Right.
And having that model lets you solve problems proactively, optimize effectively, and just generally maintain that stability users depend on. You start anticipating issues before they happen.
And ultimately, that goal is system stability, efficiency, resilience, which, as you said, is critical whether you're the admin managing the server farm or just someone wanting to understand the tech that runs, well, pretty much everything these days.
Absolutely. So thinking about how vital controlling processes is for stability and performance, it makes you wonder, doesn't it? What other low-level system components, maybe something like memory management, might be just as critical, perhaps even more subtle in how they impact everything, and equally deserving of its own deep dive?